and then if you take the quotient by the some principal torus bundle over some cover of X, not exactly X, and this cover is actually the universal, something called the universal orbifold cover of X. So let me try to give you the definition of this orbifold fundamental group and the orbifold.
This is genuine covering space or no?
No. Okay. So definition. Let's say for Z to X. Let's call this F hat is orbifold cover if, so this notion is due to Thurston. If locally F well, which is which? F is the form U tilde mod gamma to U tilde mod G, where gamma is finite subgroup of G. So this is not a genuine cover, it could be branch cover. So example is, say, C2 going to C2 mod Z2 is orbifold cover, and you know this map, sorry, yeah, okay, or let's just take C, okay, and then Z, or the coordinate W goes to W squared. All right, this is an orbifold cover. Now Thurston proved that. Okay, so first of all, what is it then? A universal orbifold cover. Okay, so definition again says that Z to X is universal orbifold cover if for any orbifold cover Y so let's give it some names. So there exists orbifold cover Z to Y. So basically it's a orbifold cover of any orbifold cover, okay? Such that F hat is the composition of, so you go down to Y and then you go down to. Now this is, you know, very tricky theorem of Thurston. That orbifold universal cover always exists. Okay, and the DAC transformations of the orbifold
and of course unique, right?
And unique, of course, and is unique. definition, deck group of orbifold universal cover is called pi1 orb, that is orbifold fundamental group. Of what? Of the teardrop is itself. Yeah. So if you have P and Q co-prime, then it's itself. If you have common factor, then you have, yeah. Okay, so this is essentially kind of good for, this theorem is good for manufacturing examples where, you know, orbifold universal group is 1. So as an application of this concept, we can do the following. So let me erase this. Here is an application of this concept. If you have x y mod g, y manifold x, g finite group, then let me see if I yeah. No, maybe I'm wrong. Let me state it correctly. Okay. Okay, so far I'm right. Then the following sequence is exact. What is this? 1 going into pi1 of y, going into pi1 orbifold of x, going to g. So this means, right, so this would seem kind of natural, right?
So you have x above, and then x also has a universal covering.
Yeah, so
So you have y above it, y above the universal covering. So that covering looks like.
yeah, so basically it just says that, you know, pi1 orb, of course the universal cover of y would be the universal orbifold cover of. So this is a very natural sequence. And now if, so this implies if pi1 orb of x is trivial, then there cannot be such a description with non-trivial g, right? So then x is not global quotient. That is, x cannot be quotient of a manifold by a finite group. So that exactly what happens with the teardrop. So example, pi1 orb of sphere with one orbifold point, this is 1. So that cannot be written as quotient array. And with Quasitorics, with that theorem, you can produce lots of such examples. Okay? And one of the things that we
S2. One point is multiplied by P, and the other is just multiplied by
yeah, smooth. Yeah. Okay. Yeah, any integer will work. So you have, say, cyclic Zn singularity here.
So in other words, you have CP1 with two.
This is a weighted CP1.
Yeah, weighted CP1.
Weighted CP1.
So you can just.
Yeah, analytically, some people get confused because analytically, this is not a singularity.
No, but I don't think it's a weighted CP1.
Huh? This is exactly weighted CP1.
Doesn't it have two singular points?
No, no. Oh, no.
Oh, it's a special case of weighted.
So
No, this is weighted
so in one coordinate.
weighted P1N. Okay. Now with Quasitorics, you can make lots of examples. And from this diagram that I described, you saw that this orbifold universal cover was sitting in the middle, like the quotient from the moment angle complex. So the orbifold universal cover of Quasitoric is also Quasitoric. Orbifold universal cover of a Quasitoric orbifold is again a Quasitoric orbifold. Okay. So that was kind of digression. So let's come back to this four-dimensional. Oh, now I have to make some remarks that formulas for rational homology, cohomology ring, of Quasitoric orbifold is same as that of Quasitoric manifold. Okay, the only difference is those formulas work for integer coefficient. Here you have to do Q coefficient. So that's also the same reference. And because of your remark about the moment angle complex, now I remember that a stable, almost complex structure exists on Quasitoric orbifold. So just go down from the moment angle complex as usual. Okay. So you can define Chern classes and everything. All right. So now I go to this four-dimensional Quasitoric orbifolds. So P is a polygon in R2. All right. So polytope just becomes polygon in R2. Okay. X is N is Z2, Z plus Z. Okay. Okay. Now what I want to do is give you some smooth chart, because in the end, whatever maps I define, I should kind of show that these are smooth maps and so on, and also the okay. So let P1, P2 be standard coordinates on R2, and Q1, Q2 coordinates, the angular coordinates that is coordinates on n tensor R with respect to some fixed basis of n. So you fix some integer basis of n, and then okay. Now, so locally, what you have is UV, if you have a vertex of the polytope, is homeomorphic to a cone. So locally inside your polytope at the vertex V, you'll have, I'll call this cone sigma of V. This is sigma V. And these edges I'll call F1, F1 and F2. Such a way that the clockwise angle between from F1 to F2 is less than 180. And the characteristic vectors, I'll give them names lambda 1, lambda 2. So I want to, XV of course is UV cross Tn mod this.
So UV is a subset of the polygon, right?
Yeah, UV. Yeah, UV is. Yeah. Yeah, UV is the subset of the polygon. Okay. So I want to give some, smooth or whatever orbifold chart explicit for this XV. Okay. Now first, let's look at the the best case. So this is standard case where you have these edges to be you have the first quadrant. Okay. So this and the characteristic vectors are lambda 1 is 1 0, lambda 2 is 0 1, and sigma of V is just the first quadrant, and this homeomorphism from R2 plus R2, okay, this is stupid, R2 cross Tn to C2 is given by, so this edge is P2 equal to 0, this edge is P1 equal to 0, and this is given by homeomorphism by P1 Q1, sorry, P1, yeah, P2, Q1, Q2. So from the R2 and torus coordinates, you go to C2 coordinates by square root P1 e to the 2 pi I Q1 square root P2 e to the 2 pi I Q2. Okay, so this, I don't know where it appeared first, but Symington's paper. Square root is needed for smoothness. Any other power will not work. So there's
The smoothness at the bottom.
yeah. So when you make transition functions from one vertex to another, only square root will work. This kind of yeah, that. Yeah, we always write. So now for a general situation.
You can use
Yellow?
No, I'm
Oh.
saying it's
Oh, that's
this is
cleaner.
so what you do is you just write it and then
What about directly? No?
directly is okay, but I think it's more convenient.
Okay. Thanks. Okay, thank you. So here in general you have F1, F2. Okay. I'll call this okay, this edges P1. Okay, P1 should go along this P1V equal to 0, P2V equal to 0. This is lambda 1, lambda 2. Okay. And this is the cone which I call sigma V. Okay. And P1 PIV is some PIV. First of all, you need to choose in such a way this is positive inside sigma V, because it will come under the square root. Okay, and PIV, how does it look? Well, it's just the equation of the line. So this is some oh, because I will do transition from one vertex to another. So right away I'm putting V.
P is a function, so it looks like you are evaluating it.
Yeah, I have many such functions. Such a way. Yeah,
V is a function. Right? V, your V is like an index.
V is like an index.
Yeah.
Do you want me to put it on top?
But that's okay. If you put parentheses, then it looks like it is.
Oh, sorry about that. Yeah, maybe I should change that somewhere. So AI P1 minus alpha plus BI P2 minus beta. Right, it's an equation of the lines. Okay? And, okay. Let Q1, okay. I lost my chalk. Let theta 1 Q1V. I don't want to write Q1V all the time because it takes more effort. So I'll call it theta 1. This is okay. Q1V theta 2 equal to Q2V. B coordinates of Tn with respect to the basis lambda 1, lambda 2 of n. Tensor R. Okay, this is not an integral basis of n, but this is still a basis of n tensor R. Okay. Now, then, I can write Q1, Q2, the original basis as lambda 1, the matrix lambda 1, lambda 2 times theta 1, theta 2. That's, and of course I can express this theta 1, theta 2, this is the new Q1 viz as lambda inverse Q1, Q2. Okay. Now with this we define a homeomorphism from xv tilde into C2. So homeomorphism xv tilde to C2. So from this orbifold chart, the upstairs space into C2 by Z1V. So I want you to look at the board now. Z1V is kind of the coordinate that increases radially in that direction. Okay? And Z2V is the one that will increase radially in that direction. So in Z1V, okay, so here is the direction where P1V increases. Okay, so square root P1V e to the pi I 2 pi I, what is Q1, that is theta 1. Okay, and similarly, okay, Z2V So to figure out this, I have to invert that matrix. That's it. Okay. Now let me show you I will write Z J. Is xj plus yj, right? So this z1, z2, you think of it like that. Well, anyways, so what is action on GV on, so what is GV? GV is n, right, divided by the submodule generated by lambda 1, lambda 2. Okay? So this is, so any G in GV is represented by a vector A1 lambda 1 plus A2 lambda 2 in N such that A1 and A2 are in Q, right? Because if they're in Z, then of course that element is 0, because this is quotient by this submodule. Okay, so G, then G action on theta 1, theta 2 is just theta 1 plus A1 theta 2 plus A2. So those are the coordinates, and you have the natural action of n, and that's how they translate. And so G action on Z1 V, Z2 V is e to the 2 pi I A1 Z1 V times e to the 2 pi I A2 Z2 V. Okay? So that's okay. So that's all I want to say. Now I describe what is an almost complex structure on a four-dimensional quasitoric manifold first, and torus. So basically, yeah, we have a preprint on the archive. It has mistakes. So now we have a new approach, and that's not posted on the archive yet. So, but credit goes to this work of Quasitoric, who recently showed. So. Last year, he showed that there exists Tn invariant, almost complex structure on any positively omni-oriented quasitoric manifold. Okay. So we'll use his basic idea that you should restrict to some orthogonal, almost complex structure. So omni-oriented. Oh, there's some technical thing. Anyways, I don't want to define it in general. I'll give you the. So let's see. Well, what it means is that all these determinants are positive.
So, yeah, for example, CP2 connects them. CP2 doesn't have that one.
Yeah, it's not positively omni-oriented. So, so definition. Okay. So example is that, or definition for four-dimensional. Okay. So X is positively omni-oriented if there exists choice of sign for characteristic vectors such that determinant lambda 1, lambda 2, determinant lambda m minus 1, and lambda m. So you have the polygon lambda 1, lambda m, lambda 2. Okay. Okay. So let's discuss the four-dimensional case where actually you don't need his, he developed some homology to correspond to this obstruction theory. But we don't need all that for four dimensions. It's pretty simple. So let's okay. So for V, say isomorphic to R4, let JV equal to set of all complex structures So the key thing is you put some metric and you only look at almost complex structures that are orthogonal with respect to that metric, and then you have some easy consequence. So V on V respecting metric. So here metric means some inner product on V. So you fix some inner product and then you do this, and orientation. Okay. JV. So with respect to that inner product, JV is as a homotopic to SO4. This is true in general, but I'm just focusing on two dimensions. Okay, and now this, in this special case, this is homotopic to S2. So this is that's not so hard to see. You can start with orthogonal matrix. The first column is S3 and keep on arguing like that. It will be S3 cross S2 cross S1, and this one is just S1. Well, this one is S3 cross S1. So the unitary, the first vector has to be in S3, and once you do that, you have to look in the complex orthogonal plane. So the next one is in U1. So downstairs is S3 cross S1, and upstairs you can see is S3 cross S2 cross S1. So, but this is now this is okay. This is simply connected, and that is of tremendous advantage. Okay, now this is what you do. You so X four-dimensional Quasitoric. Okay, fix and omni-orientation. Okay, suppose so let's say X is four-dimensional, positively omni-oriented. Quasitoric manifold. You fix Tn invariant metric on X, Okay. So for each vertex, so you have some picture. This is P. So for each vertex, okay, so dots, each vertex choose J in neighborhood of each vertex such that J is given by Tn action and omniorientation. Basically, you have this normal bundle decomposes into, right, the circle directions, and you use the S1 action to define J. Okay? And then J is, because your metric is Tn invariant, then it will automatically imply that J is T is orthogonal in these neighborhoods. Now, so near the vertices, you construct J locally, right? You can do that. Then you extend over the edges, okay? Then what you do is, if you have an F, you extend it over every edge. That you can do is, you see, let new F, okay, new F be a tubular neighborhood of pi inverse F. So some piece of the Quasitoric there, and the tangent bundle of new F, of course, tangent bundle of the underlying sphere plus this normal bundle. The bundle, this is the principal as, corresponds to S1 bundle. Okay, and now what do you have? You have in the vertex, these are the two directions, okay, and your J. So what you do is, okay, so positive omniorientation implies J extends over new F. Basically, they just match. If you well, if you have this TS two directions, so yeah, and you have this. So the normal directions and the TS two directions. Okay. Well, Okay, let me not get bothered by these details. Okay. And then
What's your goal? I mean, since you don't
no,
know.
no. So I first want to put in torus invariant almost complex structure. So it's not. I mean, you have a stable almost complex structure, but I just want to give you an idea of how to do it how to construct an almost complex structure first. Okay?
But that's a negative, because it's a manifold, right?
Yeah. All I will say is that you do similar thing for orbifold. Okay? And because there it's more complicated, so I don't want to really bother you with all those details. So now extension obstruction to extension of J to pi inverse interior of P. So here is something nice observation of Quasitoric. What it says is that your almost complex structure is going to be torus invariant, right? So all you need to do is to extend it on the polytope. And then you can get it by just a rotation on the entire. So this is pi 1. So you have it defined on some loop here, and you just want to extend it. So pi 1 of this set, SO4 by S2 by U2, and that is so no obstruction. Okay, so I will just say that this so similar construction of Tn invariant almost complex structure is possible for Quasitoric orbifold, for four-dimensional positively omni-oriented Quasitoric orbifold. Okay. But this as such is not good for me. I mean, not good enough for me, because I want to have some of these maps, right, blow-down maps between two orbifolds. Individually, I can give them almost complex structures, but I want to argue that I can do it in such a way that the map is almost complex. Okay? So I have to do some extra work. This as such is not enough for me. So let me define what is the blowdown, and I don't have that much left, so so what is the blowdown? So I will consider the simpler case where I have a manifold to blowing down to an orbifold. And what do? So in picture, this is how it looks. You whatever it is. From there, what you want to do is delete one of the edges. Okay, so basically you want to go from this. Let me close this up. You want to go from this to this picture. Okay, and now this you have say lambda 1, lambda 2, lambda 3. Maybe pairwise they form basis of Z2, but when you remove lambda 2, lambda 1 and lambda 3 no longer form a basis of Z2. So okay, now introducing this opposite operation, going from here to there, you can do it by a connect sum, right? So I'm trying to do the opposite thing, okay, to a connect sum. So this would be the direction of the map rho, and I'll give you this what are my model for these things. I'll right away draw a bigger picture. Okay. Whatever there is. Here is the edge P1 equal to 0. Here is P hat equal to 0. Here is P2 equal to 0. Characteristic vectors are -1m, 1, 0, 0, 1. So orbifold singularity here of order m. Going down, no orbifold singularity. If you look at this two determinant is 0 times m minus 1, so no orbifold. So this is manifold. Okay, I want to go down to this picture where I have, so this is V1, this is V2. I have this picture. Secretly, I hope to do this. Where this is new vertex is called W, and this things are called new coordinates for the polytopes are R2 and R1, and characteristic vectors are 1, 0, -1m. So now W would correspond to an orbifold singularity of order m. Right? These two don't form a basis. Okay. So I want to go down this way. Okay? And what I do is the following. I will, at the angle level, Q1, Q2, the angular coordinates I won't change. Only these radial coordinates I will change. And the rate, so I'll bring this line down to a point, shrink it, and everything depends on the rate at which I shrink. So what I do is I choose two neighborhoods. Okay. Outside this, nothing happens. No radial change. Inside this, I will tell you how to do it. So what I do is I fix I fix an epsilon 1 and an epsilon 2 0 epsilon 1 very small, okay, and the rate at which I will shrink is given by a function, smooth function of one variable if t is between 0 and epsilon 1, and this is 1 if t is bigger than epsilon 2. And the map rho, so let me give this polytope some names. So this is like the epsilon 1 neighborhood, and this is the epsilon 2 neighborhood. Okay, and so this line is p hat equal to epsilon 2, and this line is p hat equal to epsilon 1. And I call this polytope capital P, call this capital P, I don't know, bar. Doesn't matter, I may not need them. And rho from P cross Tn modulo this I'll call, say, the what do I call this, x, and going to this P bar cross Tn modulo equivalence relation called y, and rho has a very simple formula, rho of P1, P2, Q1, Q2. This is given by delta P hat P1 delta P hat P2 Q1 Q2. And let me just write down what are the coordinates you have. So what's happening, this any point on this line P hat equal to 0 would go to, this is of course the value of R1, this is the value of R2, so we'll go to the origin. So basically the entire sphere there would go to a point. Okay. Now let me write down the coordinates at these 3 points, and then I'll write rho in terms of those coordinates. So this is some the first one is okay. So the first vertex V1, you see when you go in the upward direction, then this P hat is the measures how your radius increases. So there's no other mystery there. Okay, and V2. So in V2, P hat and P2, so when you go in this direction, okay, let me just copy what I have. P hat So these angles are obtained by, you see, you take this, at V2 you take this matrix 0, 1, minus 1m, and you invert it, and you will get m1. Let me copy. So that's how you are getting these coordinates, and minus 1, 0. So here it would be like P2 e to the 2 pi I minus Q1. Okay. And similarly now for W, so here is one, here is one, and here is the other. Now I write rho in terms of these coordinates, and then I'm pretty much